Okay, here we are. Let's talk about the take-home for the first few minutes. How's it going? Do you have any general questions? I got a couple of emails that I responded to, but I wonder if anybody has any specific questions. Yeah?
On the second problem.
Second problem?
You say the output should be y equals products of weight times space. Is there not going to be a sigmoid there? Or is it just product?
Well, you recognize that the output of the neuron is run through a sigmoid, right? So therefore, the input I think we've been calling A, the activation to the neuron. The output has been called Y. So you can use the result after the activation as just a Y. Just call it Y. Yeah. Does that answer your question, you think?
I think it does.
Oh, good. Okay, such a deal. Any other questions? Yeah.
On the fourth one, do we know what a sum product complement is? It talks about sum products and all that.
Let's take a look at this. This is number 4. You know, I don't know if they're going to be able to capture this on the TV screen, number 4. It says, consider the Zada union and intersection of two given fuzzy membership functions. Can you find two different membership functions? That the result of the sum product intersection and union gives the same membership function as the Zada intersection and union. So your question was what?
Do we know what like the sum product complement is?
We did. I don't think you need to know that in order to do the problem. But if you want to use the sum product complement, it would be 1 minus. Use the Zada complement if you have to use one. Yes.
Number 3 says look at page 51. There's some numbers in the slide. They're like 15
Okay.
notes or something. Do you specifically want us to use those 15 notes? Like
No, I don't want you.
15 or just in general?
Okay, so the question is on problem 3, do I want you to use those exact 15 nodes? No, I say using the indexing illustrated in figure 5.1. So it's just an illustration of the manner that we want to do the indexing. In other words, don't go to the layered sort of architecture, but rather number the neurons sequentially and make sure that smaller ones feed the bigger ones. Yeah, that's all they meant. And if you do that, it's a very nice way of putting things to make the math very easy. Makes it very tractable. If you do it in layers, if you've thought about it, you have the number of layers, which layer it is, which input it is, and your weights turn out to be like 6-dimensional or 3-dimensional or something, as opposed to the simple 2-dimensional, which comes out with this architecture. So you just get embroiled in subscripts if you do it the other way, which I've done. I saw this initially, and it was a great way of doing things since it simplified things extensively. So that's what I was meaning. Yeah.
Problem 2, you said you wanted the answer in terms of y, t, and I, and I was wondering if that was maybe supposed to be y, t, and w.
Oh, yeah, yes, good point. Yes, because clearly you have to have the weights in there. So yes, W should be included in there. I is the input, T is the target, and Y being the output. Yes, so you do need the weights. Other questions? Yes.
You said that, I think the book said that the del AK by del AI is non-zero only if node I is connected directly to node K.
That's correct.
What if I have a node which is in between the two nodes?
No. The question is taking the partials, you only need to take into account the connecting neurons. And the question is, what about if you have something which feeds a neuron, which then feeds the neuron? What about the first and the last one? Is that your question?
Let's say if there's one in between.
Yeah, if there's one in between. No, it's because you're taking the partial. And so you only take the derivatives with things which are with variables that are explicitly stated. That's the idea of a partial, right? So therefore, you don't need to take into account things that are 2 hops away. You only need to take into account those parameters which directly contribute to the activation and the state of the neuron. So therefore, things which are far removed are things which you don't have to worry about. That's one of the mathematical beauties of the error backpropagation. If it weren't that case, then we wouldn't have that aesthetic relationship where the update of the neurons was only dictated by the update of the weights was only dictated by the states of the neurons which connected the weights. Does that answer your question? You sure? You looked hesitant. Okay. Yeah, with partial derivatives, the variable with which you take the partial, the rule is that variable has to explicitly appear in the equation for it to affect it. If it's implicit in the equation, with partials it doesn't matter, but if you're taking a straight derivative, it would. Okay? Any other questions? Okay, then I think for the Ed students, what we'll do is this, we'll end our discussion on the take-home right now and go ahead and go into the lecture material. So let's go ahead and do that. And let's kind of review where we were at. Okay, last time we were talking about Chapter 9, which were faster variations of backpropagation. We're not going to cover all of the elements in here. You could, I'm sure there has been upwards of 500 to 1,000 papers written on error backpropagation, each making its own incremental contribution. So we're not going to hit all of them in there, but we will go through a few of them, and we did last time. I think we talked about the Fallman's Quick Prop, which is available on the software I made available to you, where Newton's method is used for finding and minimizing f of x through a Newton update. And then last time we talked about Jacob's delta bar delta rule, which was on page 137, which took into account the heuristics in terms of a search, that if you're on a very flat surface, then you wanted to take very big steps. If you're on a very steep surface, you wanted to take itty bitty steps. And what Jacob's delta bar delta rule was, took these heuristics and attempted to place them in a manner that was implementable to dynamic updating to each one of the learning rates of each one of the neurons. There is in the book, this classical book, an entire chapter on optimization. In which the classic ways of optimization are presented. One of them that we're going to go over today is the idea of simulated annealing. Simulated annealing and genetic algorithms are the ways that are the two topics that we're going to talk about today. Simulated annealing actually has its origins from metallurgy, wherein people in metallurgy, which is a field I don't understand, found out that if they lowered the temperature of a molten metal at a slow rate, it got different properties than if they lowered it at a very fast rate. The example which is often given is of cooling water into ice. If you lower it really, really slowly, you get ice which is very, very clear, whereas that if you freeze the ice very, very quickly, you get ice which has cracks and such in it. So the concept is that this concept of annealing would be applied to optimization. It actually is in the area of something called stochastic optimization. We talked about a single agent, which is looking for a minimum, and we talked about steepest descent, which was the idea that you stood on the edge of a hill and you figured out which way was down. You're blind, but you know you want to get to the valley, so therefore you stand on the hill, you figure out which way is downhill, and you take a step in that direction. There are many variations of that. As we mentioned, there's people in operations research get their PhDs in these different techniques in optimization. Another technique, the most simple-minded random optimization, is as follows. You're standing on this hillside and you stick your foot out through a predetermined step size. If that step is downhill, you take it. If it's not downhill, if it's uphill, you bring your foot back in and you take another step in another direction. And the neat thing about this sort of optimization is it's really simple computationally to do. Very nice and simple in terms of the computation. Simulated annealing is something like this, but it also allows you to take a step uphill. So let's talk about this and ask why it is we would take a step uphill. Hidden Markov models again? Who was in here before? Hidden Markov models? Or just Markov? Oh, okay, so it's just Markov. And who doesn't erase their boards? What professor? Rod, okay. Okay, I'll let him know you told me to. Okay, good. Okay, simulated annealing. Now, annealing is, in metallurgy, is the process of lowering the temperature in accordance to some schedule. So when they have a molten metal, they actually have a schedule where they look at the temperature as a function of time, and they try to look at this temperature as they bring down the solid and follow the schedule. The process of doing that is referred to physically as annealing. Now, you'll notice that if one has a high temperature corresponds to something which is stochastic. If you're in a high temperature, you have a case where you're vibrating a lot, right? Your molecules are vibrating a lot. That's exactly what a higher temperature is. So we do exactly the same thing with simulated annealing. And here is the concept of simulated annealing. Is you take a random step, If it's downhill, you take it. So in other words, if it proves things, you take it. Now, with just the pure random optimization we talked about before, if the step was uphill, you didn't take it, right? But with simulated annealing, you take it with a certain probability. If it's uphill, you take with a probability of P. You take it with a probability of P. And this probability decreases the longer you're in your optimization process. Now, why would we ever want to go uphill? Well, we saw that one of the global problems with the optimization techniques was the avoidance of local minima. Gieman and Gieman, in a classical paper which is referenced in the book, actually showed that this process, if you annealed this probability, so in the beginning of your search it was a big probability, and as your search went on and on and on, your probability got smaller and smaller and smaller, so that eventually you didn't go uphill at all. They showed that if you annealed sufficiently slowly, that you would reach the global minimum with probability 1. So it's convergence in what is referred to as probability. Probability is a terrible type of convergence because it's very close to the monkeys at the typewriter sort of convergence. Have you heard the story of the monkeys at the typewriter? If you get enough monkeys at the typewriter and they're all just banging out random keys, eventually they will generate the dictionary or something like that. And that will occur with probability 1. Well, yeah, it does, but it's going to take those monkeys a very long time, unless there's a lot of monkeys, okay? So it's not a guaranteed sort of convergence. It's a convergence in probability, much like the monkey at the bicycle. But it is one of the few cases of optimization which, in any sense, guarantees a global minimization. The problem with simulated annealing, however, is that the scheduling is so slow that many times you might as well do something close to an exhaustive search. In other words, it takes too long of a time to do it with what Gieman and Gieman showed. Anyway, the probability of performing the step is e to the minus del E over t. Where E is equal to the error that we talked about previously. Now this is typically the mean square error. That is the separation between the between what you want and what you have, the output of the neural network versus the target of the neural network, so the result is squared. And you look at the error between two steps in time, and you see what the change in error is between those two steps in time. And it is with a probability of p equal to this, and this is actually loosely based on a Boltzmann sort of statistics, but this is the probability that you take a step up. Now the temperature looks much like this. This is the annealing. So in truth, this probability is a function of time. So that in the beginning, you're going to have a small value, a large value of t, and as time progresses, this is going to become much smaller as time progresses. Now what Gieman and Gieman showed was they showed that t of t, which is this annealing schedule, if it was of the form t naught over log of t plus 1, where t is your iteration step now. This is the iteration step, so in discrete time. If the annealing level was according to this schedule, that you would actually converge with probability 1 to the lowest level. The problem is that this is a very, very slowly reducing curve. In other words, it goes to 0 very, very slowly. And so therefore it's going to take you a lot of time to cook. Now you'll notice that in this case that vibration is associated with temperature, is associated with the chance that you're going to perform and take this step, right? And in the beginning, the chances are greater that you would take the step as it would as time increased. One of the analogies is that I kind of like is that you have this error surface that you're looking at which has local minima. And your ball is where you're at in terms of searching for the local minima. The analogy isn't perfect, but it does illustrate it. And in the beginning, what you do is you shake that surface a lot so that if that ball falls in a local minima, you have a very good chance of shaking it out of the local minima, right? And then as time progresses, you slow down that shaking. And if you slow it down slow enough, you are going to end up in the global minimum because, in essence, you've shaken it out of all of the local minima. So that's the concept. Simulated annealing is based upon a type of stochastic search. Anytime one has probabilities associated with your search, it's referred to as a stochastic search. You notice that steepest descent wasn't stochastic. There was no random variables associated with the search at all, right? There's no coin flipping, which is essentially what you're doing here. You're flipping a weighted coin to decide whether you stay going uphill or whether you take the step uphill or whether you don't take the step uphill. Now, another type of popularly used stochastic process is something referred to as the genetic algorithm, which is actually the topic of the next chapter, 11. Actually, is covered in both chapters 10 and 11. We're going to hop over and we're going to talk a little bit about the genetic algorithm and how the genetic algorithm works. There are a number of stochastic algorithms which fall into the area of something called evolutionary computing. Evolutionary computing differs from classical optimization in the sense that instead of just having one guy going around the hills of West Virginia, as we talked about, trying to find the lowest point, with evolutionary processes, you have 100 guys, and they're all on walkie-talkies talking to each other, trying to find the minimum. This is not the way the conventional optimization is developed. Typically, it's a single agent optimization. That's true with steepest descent, it's true with simulated annealing, but not with the evolutionary sort of processes. The concept is based on a theory based on survival of the fittest. And basically, the entire concept of evolutionary computation is as follows. We have a number of people all around, and they are at certain levels, and they're on all walkie-talkies to each other. Well, what happens is that the ones that are really high up, okay, far from the minima, or far from at least the best solution that you know about, they're not very good. Let's kill them. Okay, so we kill all these guys that are on top. They die. We just don't need them anymore because we're really interested in finding the bottom. So this leaves kind of a subset of your best results. Well, now what's going to happen? Now what's going to happen is all of these guys at the low level are going to exchange information and in some way develop offspring. We won't go with the analogy too far. But they develop offspring, and these offspring generate a new population over the hills, which is better than the first generation by using the best of the results. And so all of these new offsprings, well, the ones on top kind of die, and the ones that are lower survive, and they begin to repeat this process generation from generation, and eventually one of them is going to find the local or the global minimum. We mentioned that neural networks has many founders. Fuzzy systems that we talked about has one founder. Evolutionary computation has a number of different founders of people that have done seminal papers independent and without knowledge of the other one. One of the first people was Fogel, F-O-G-E-L, who in 1965 published a seminal paper on evolutionary, what he called programming. It's not the genetic algorithm, but it's evolutionary programming. And his idea was to be able to take a program and actually evolve the program by looking at a number of different programs and having these evolutionary swaps going back and forth. There was also the very visible Tierra project, which was at the University of Delaware, where the professor there, I forget his name, the professor there developed a program which is called Tierra. It's more in the area of artificial life. And by the way, you will hear the concept of artificial life being related with evolutionary computation. Artificial life is more of what scientists do, and evolutionary programming is more what engineers do. Artificial life attempts to computationally emulate life or different patterns of life, whereas engineers were more interested in reducing it to practice. Anyway, what the Tierra program did was generate, first of all, a special type of program where there were no bugs. Wouldn't that be great to have a program of that sort? So that every string of ones and zeros corresponded to some sort of statement. And in Tierra, what happened and what cut the world really interestingly was this guy wrote a bunch of programs, and the survival of the programs was dependent upon how short they were. The shorter the programs, the greater chance that program had to live. Well, he wrote a number of these programs, and they lived and they prospered there on the disk. But then he found out something interesting, that shorter programs began to emerge. Because what he would do is exactly this evolutionary approach. He would look at these programs, he would look at the ones that took longest to run, he would kill them off. He would take the shorter ones and make new programs by actually doing kind of a genetic crossover. He would take two programs, cut this one here, take the bottom here, put it over here, take the bottom here, put it over here, and have two different programs. Does that make sense? So it was the concept of marriage, if you will, okay, chromosome swapping. And pretty soon he found out that by doing this and also adding mutation, where he would go in and look at the bits and with a very small probability switch bits from 0 to 1, so imposing mutation on the programs. And this artificial life began to percolate on his hard drive, and pretty soon he found out that he had smaller programs than he thought was possible. And he looked at them and said, wow, this is really neat. And don't forget that he was able to write this new program in such a way that no matter what you did, no matter what string you were able to get, it was indeed a program. I don't understand how he did that, though. Yeah.
What is the program doing?
What it's trying to do is evolve programs which are optimal to live within that environment. See, the concept is survival of the fittest. What is fittest in this sense? Fittest is the shortest program. So it's trying to evolve very short programs that can exist within this environment. And if you Google Tierra, you'll find the program which you can download and play with. But anyway, the next aspect was he found that there were even shorter programs, but he looked at these shorter programs and, my goodness, they weren't viable. And he found out that they had found a way to parasitically attach themselves to longer programs. So therefore, they were very, very short, but they were parasitic on the other programs. Well, eventually, what do you think happened? It's like too much taxes, right? The parasites began to totally take over the longer programs. Pretty soon the longer programs died out, and it was populated primarily by parasites who couldn't survive. Well, then what happened was that in addition there were some of these programs which evolved that had actually developed immunities to these parasites, and the parasites weren't able to attach themselves on it. So this was the process that was seen in the evolutionary sort of way of doing things, and probably the first artificial life, demonstrated artificial life sort of program, and it was very compelling. It's a very, very compelling sort of argument. Well, let me tell you then how we can apply this to search sort of problems, number one, and number two, how we can apply this directly to the training of a neural network. And we're going to talk specifically about genetic algorithms. In the area of evolutionary computation, there's a new journal called the IEEE Transactions on Evolutionary Computation. It's only been out for, I think, about 3 years. And so this is where people in IEEE go to do things. So IEEE, what did I say? IEEE Transactions on Evolutionary Computing. Okay, that's what it is, evolutionary computing. So we have the idea of evolutionary computing. Genetic algorithms is only a very, very small part of that. And I think that there's a lot of attention given to genetic algorithms because that was the first viable engineering package which was presented to the community, and everybody looked at it. And they said, wow, this is great. Another thing, genetic algorithms are kind of like optimization for dummies. You know, these little dummies books you get out here. You notice the fuzzy logic, if you don't have too many control variables, is kind of like control theory for dummies, right? Because we can really do it quickly, and you can teach somebody these fuzzy control sort of aspects in just 2 or 3 lectures if they have an engineering sort of background. They don't have to have an entire PhD in control systems and no Laplace transforms and LQG control and all of this highfalutin stuff. It's very heuristic and very applicable. Genetic algorithms are like that. They're very easy to understand, and they can do optimizations. Is it the best way to do optimization? It depends on what you mean by best. In many cases, you're going to be able to do optimization a lot better if you hire somebody who specializes in that, and they come in and look at the problem, and they will figure out the best algorithm to optimize it. But if you just want to do it yourself on your PC, over a 2-night, 3-night period, genetic algorithms is a good way to do it. It isn't the slickest, neatest way to do it, but it works. So genetic algorithms is one of the subsets. Another one is the area of evolutionary programming. The Tierra software is subsumed in the area of evolutionary programming because it involves actual programs which are swapped in an evolutionary sort of sense. There is also the area of evolutionary strategies. Wherein there is only one agent, but that agent is looking at a way to explore the space in some stochastic way. Simulated annealing would be an example of evolutionary strategies. And then there's a number of other things. As you'll see, after we develop genetic algorithms and talk about a little bit, you'll find out that we have a wonderful ability to just heuristically take this concept and adapt it to our own problem. It's a very easy paradigm in which to place domain expertise and insight into the solution of the problem. There isn't just a simple cookbook. It's more rather of a strategy of solving the problems. Well, let's go with genetic algorithms and talk about genetic algorithms, specifically evolutionary computation in general. All of these are, first of all, only applicable to cases wherein the final solution exists in some sort of smooth solution space. There are many examples where I think it'd be a big challenge to find an optimum or perform a design based by evolutionary computation, because some solutions are irreducibly complex. They're irreducibly complex in the sense that if one takes that solution, whatever it is, that design, and one is to remove a single component of it, any one of a number of single components, the whole thing shuts down. There's a number of examples in biology concerning that. I think one of the coolest generic examples I've heard about is I've heard proposed for irreducible complexity is a simple mousetrap. You have a mousetrap with the classical spring and the bar, and you wonder on an evolutionary scale how that could have evolved gradually, because you have a solution there which is irreducibly complex. If one was to remove a staple or a bar or any one of the aspects, the whole design of the mousetrap would not work. It is not something which can be designed by a gradual evolutionary sort of procedure. So that's one of the assumptions here, is that the problems that we are looking at are inherently smooth and have the ability to be solved in a manner which allows for gradual improvement. Typically, such problems are characterized by smooth error surfaces, right? You have to have smooth error surfaces. And you can actually find better solutions than other solutions. Another example of things which probably don't work too well in evolutionary programs are combinatorial search problems, wherein you're required to go through all of the different combinations in order to find the best result, because there is no underlying smooth surface. Fortunately, there are a number of cases where we do have these smooth surfaces, and in such a case, let me elaborate on that. The distinction between regular computation or optimization, this is general, and evolutionary computation is that in both cases we have the ability to have some sort of error surface here, exemplified in 2 dimensions, with which we are looking for the global minimum in some fashion. With steepest descent and simulated annealing and such, you have one agent, again, which is going around trying to find the minimum according to some process. The second case with the genetic algorithms, you have numerous agents going around, and all of these agents, number one, have a certain position which is associated with them, but they also have the ability to talk with each other in some fashion. So all of these agents are kind of moving around looking for the minimum. You can see why evolutionary computation has only come into vogue in the last few years. We've only had the computational power to handle numerous agents in more recent years. Whereas before, when people were talking, even before the personal computer, this was a very developed field, but they were using those old IBM mainframes, which were incredibly slow, and so they did not have the computational wherewithal to determine the interchange and coordination of a number of different agents. So here's the concept that we are going to apply for cases where we have such smooth error surfaces. The first thing we are going to do is we are going to compute the fitness to put this, by the way, in the vernacular of evolution and talk about concepts such as survival of the fittest. Fittest usually means good. We're trying to make things big, whereas before we've done things which are small. So we're going to be talking now not about finding the minimum, but rather finding the maximum of a area, of a curve. Typically, if you have an error surface, usually if you raise it to e to the alpha, that's a good fitness. In other words, any monotonically decreasing function, you can take an error surface that you want to minimize, transform it into a fitness function which you want to maximize. This is the most common way that I've seen of doing it. So we want to find the fitness, so we're actually in West Virginia not looking for our home in the valley, but we're looking for the mountaintop, right, in order to find the maximum. Everything that we've talked about, by the way, is applicable to fitness functions. Instead of steepest descent, we would have steepest ascent. And in fact, there are some optimization courses that don't teach steepest descent. They teach steepest ascent because they're doing fitness functions. But nevertheless, we're finding the maximum here. So the first thing we do is compute, and we rank the fitness of each one of the elements here. So clearly, if this is the mountaintop, these guys are not going to be very fit, right? Because they are going to have a low fitness function which is associated with them. So what happens to those low fitness functions? They die, right? Okay. So the second thing we can do is we kill the weak. And we kill the weak. We actually don't kill the weak, but we do something which we call the survival of the fittest. That sounds Darwinian, doesn't it? How many T's in fittest? Okay. Oh, 2. I see. 3 or 2? 3. Okay. Survival of the fittest. And we do it in the following way. Suppose that we had in our population, we had 4 agents, okay? And by the way, in genetic algorithms, the agents are referred to as chromosomes. So suppose that we had 4 chromosomes, and the fitness of these 4 chromosomes was the following. It was 87, 12, 4, and 2. Okay, clearly this one really has a nice fitness associated with it, right? Well, inherent in the actual running of this, we do have some preliminary things we should mention. Number 1 is that we need to choose the number of chromosomes that we have. And secondly, for genetic algorithms, we code these as 0 and 1s. Now what's interesting is it doesn't matter how you code it as 0s and 1s according to the genetic algorithm purists. You can take these results and you can use the Boolean expression, like 3 would be 0, 1, 1, or 4 would be 1, 0, 0. You can do it that way. Or you can use something called gray codes. Are you familiar with gray codes? Where you have a Boolean sequence, and each sequence has kind of the same number of 1s and 0s, and there's an equal importance between each 1 and 0. If you use a conventional Boolean expression, the very significant bits dominate over the very non-significant bits. Gray codes are a Boolean representation to where each place, each 1 and 0, has the same sort of flavor. So we code as 0s and 1s. The matter that you do this, it doesn't matter, according to genetic algorithm people. So anyway, we have these chromosomes, and we compute the fitness. So this is, if you will, like the space we're trying to optimize on, and this is the result of the fitness. Now, in order to choose the next population, we are going to choose the next population stochastically. And we do this by taking a wheel of fortune, and we are going to divide it up into 4 different places. We will divide it up into 1 where 87 corresponds to the percent here. We have 12 at this point, and then I know it isn't perfect, but we have 4 and 2. And if we call these A, B, C, and D as the names of our chromosomes, we would have A, B, C, and D. You get the idea? So we take a wheel and we make the arc length proportional in percentage to the individual fitness. Okay? Now what we're going to do is that in this case, since we have n is equal to 4, we are going to spin the wheel 4 times randomly. Whoop. And once it stops, whatever it's pointing to, that will be our next population. So the next thing we might do is survival of the fittest. We might spin the wheel the first time, we might get an A. Spin it the next time, we get an A. Spin it the next time, maybe we get a B here, and then we would get an A. I better get a C here, for reasons which you'll see. Now, typically you don't use 4. You use maybe 100. Okay, no reason you can't use a lot of them. I'm just doing this for pedagogical reasons so that we can follow the explanation. So this is survival of the fittest, and I think you can see that if there's a big fitness, you have the ability to survive better, right? And this weak guy here, this D, chances are very good that it will die out. Not 100%, but it's very, very good that D will not survive into the next generation. So that's how we do the survival of the fittest. The third step is one called crossover. Okay, go ahead. Question?
This is completely stochastic. Isn't it possible that you could kill yourself right off the bat with 4 Ds?
Absolutely. You could. In which case, there's not much future for your youth.
So there's no guarantee of convergence on this method.
Okay, let me tell you one of the common things which is done. One of the common things which is done is what's referred to as a king of the hill strategy, wherein you keep your strongest neuron and you make sure that it goes on to the next generation. So the king of the hill will assure this strategy. You can also do a modified king of the hill where you take your 3 biggest and keep them unperturbed to the next generation. So in such a strategy, you do have that probability of getting exactly the right answer. But even if you got all D's, it would still work. I'll show you why. Because crossover is very interesting. Crossover takes the binary strings. Say, for example, we had A and B. And let's say A, what did we say its fitness was? 87. And B had a fitness of 12. Okay, well, this is the fitness. This is kind of the output, how far you are above ground. And the coordinate that which the agent exists is given that by the binary string. So we have a 1, 0, 1, 1, 1, 0, 1, 1, 0, 1, 1, 1, 0, 1. Now, say this was, for example, the training of a neural network. These first 5 might correspond to the values, maybe a floating point value for weight number 1. These would correspond to the values for weight number 2, etc. Okay? So you can actually optimize over a number of different variables just by slapping them side by side together on the evolutionary, on the chromosome. So we're not restricting ourselves to just one variable, but these are a string of 1s and 0s corresponding to the chromosome, an encoding of the variables over which you want to optimize. And then, of course, B is going to have a different value. Maybe something like this. Crossover occurs by pairing up the chromosomes, unlike chromosomes, and choosing a point referred to as a crossover point randomly between the first digit and the last digit. So it's another stochastic nature of it. So we have, I don't know, some sort of point that we choose. And again, it's a random number. Now, what we are going to do now is we're going to take this part of the chromosome, and we're going to put it up here. We're going to take this part of the chromosome, put it down here, and we are going to come up with new chromosomes called A prime and B prime corresponding to this result of the crossover. Do you understand the concept? So we choose a point at random, and then we swap so that A prime would be 1, 0, 1, 1, 1, 0, 1, 1, 0. And then we would bring these up here. 1, 1, 0, right? And on the bottom, we bring these down here. So we choose an arbitrary point, we do this, and this is referred to as crossover. And you can see the weak analogy to offspring, right, with 2 parents. So weak analogy. So this is the concept of crossover. And then we have mutation. Mutation. Mutation occurs by going through the new population and with a small probability flipping a bit from a 1 to a 0, or a 0 to a 1. Okay? So with a certain probability, we might have A double prime be 1, 0, 1, 1, 1. Well, here's A prime. And we might go along here and say, keep this one same. Say flip a coin, which is maybe has a 10-fold probability of coming up. And so roughly every 10th value you would get a 1 turning into a 0. So this would mutate to a 0. And B double prime would be the same. And so we go along here and we go, oh, okay, this one becomes a 1, and maybe this one becomes a 0. So with a certain probability, the 1s get flipped to 0s and the 0s get flipped to 1. This is the concept of the mutation. What's the probability you choose? Much like your population, the mutation is a parameter of the design. But you can also see this probability is something that you could anneal, couldn't you? And maybe you could get the same sort of flavor of results that you did with simulated annealing. In fact, some have proposed that with a very small variation, a genetic algorithm with 1 chromosome is equivalent to simulated annealing. It's very close to simulated annealing. But we could, for example, take this probability and actually, again, anneal it to start out with a very, very high probability of mutation, and then as time progressed from generation to generation, begin to decrease this. And we're done with the mutation. So what do we do now? What do you think we do now? We go to 1 and repeat. And each time the process goes through this, we have a different generation of chromosomes. And by survival of the fittest in step number 2, we're hopefully keeping the most fit of the neurons. We're keeping the most fit to the solutions. We're throwing away the bad solutions. We're letting the good solutions exist with a greater probability. We're allowing information about the good solutions to actually swap with respect to time, and also mutations to put this very nice stochastic flavor in it, which smacks of simulated annealing. And this is the basic vanilla genetic algorithm. And it works very nice. One of the things is it works much nicer on cases where you have a glut of false minima, where a steepest descent would kill you. There's a classic result in a book by Goldberg, which I'll bring in, which actually has a sinusoid which is modulated. So the sinusoid actually goes like this. I'm sorry. And the actual global minimum is right here, and the other things are just local minima. This would be, you go crazy trying to get this by steepest descent, right? Because you get stuck in false minima quite a bit. And you can see also the value in a air surface, air landscape like this of, you would see the value of simulated annealing to shake you out of the local minima in some sort of fashion. But genetic algorithms, it turns out, works very nicely on problems like this. Very nicely on problems. Question?
How do you know when to stop?
That's a good question. How do you know to stop on any optimization program? How do you stop on steepest descent?
Idea.
Okay. Remember that when you're doing optimization, you're doing it for an engineering purpose. Typically, you will have a constraint placed on you for the optimization. That is, you require a certain adherence in order to fit into the problem that you're looking at. In most cases, that degree of agreement or your error is pre-specified even before you begin to do the optimization. It's pre-specified. So if you get to that point, you're done. Okay, so that would be one way to do it. In other cases, you just want to get as good as you can. This is what students do, right? And Ivory Hall academicians. You just want to get to a solution which is really, really, really good, best you can do. Well, in that case, but you don't want to spend forever doing it either. One way to do that is to monitor your error. and if the error doesn't change perceivably over, say, 1,000 generations, or in steepest descent, 1,000 epochs, then you're done. Okay, you're not going to get any better. Then there's the other things you can do is shake them out of the minima and things like that to try to get them better. So these are referred to, by the way, as stop criteria. Any iterative algorithm that you have such that you are not knowledgeable of where you want to be, you don't know where you're at. So you have to have some sort of stop criteria. I believe in QuickNet they have a number of stop criteria, as Ben mentioned, and the algorithm actually stops when you've achieved one of them. They're connected together, kind of we'll stop if this happens, or this happens, or this happens. So those are 3 stop criteria that could apply. Okay. So the answer is it's very problem dependent, but I would caution you that most engineering applications, the resolution that you need to achieve, the accuracy that you need to achieve is pre-specified by the problem you're working at, and therefore is set before you do it. And if you get that, hey, you're in a local minimum. So what? You got a solution that you can use for an engineering application in the business world or whatever. Okay, any other questions on that? Yeah.
When I run a GA, I use like a King of the Hill type thing, but I had a problem where the King of the Hill basically became the parent eventually of everyone in the generation. Well, you hit like a local minima pretty easily if it happened to be a local minima.
Yes.
And all I found, the only solution I came across very quickly was to actually purposely keep really bad parts of the generation.
To keep very, very bad parts of the generation.
It's sort of like because mutation just wasn't strong enough, and in order to just mix it up hard, you had to keep like 1 or 2 really bad fitnesses to try and jump the local minimum.
Okay. So the concept was, if I could repeat this, in your experience, by the way, I've heard very mixed results using genetic algorithms. There's people that totally hate them because they say they can't get them to work, or that they're very close to exhaustive search. You got to let them run that long. There's other people that love them and think that they're really, really wonderful. So go figure. A lot of it is in the smithing of your parameters. For example, one of the ways to address the problem which you talked about, which was at the King of the Hill. Now, the King of the Hill is the following. You choose the best result and you keep it through unscathed to the next generation. And you keep the King of the Hill through everything. So you don't marry it, or you can marry it, but make a copy of it before you marry it. Okay. And in your case, you said that eventually this became the parent of all of these different ones, right? And so you were stuck clearly in a very deep local minima that was hard to shake out of in terms of that. There are a couple of things you could do. Whether they would work in your specific case, I can't say. Number 1 is to increase the number of your population, and number 2 is to increase your mutation rate. Increasing your mutation rate would give you the idea of hopping around more, a lot of heat, knocking things out of local minima, a lot like the simulated annealing. So those are 2 of the different parameters that you could affect and do this. Okay. Any other questions? Do you see why they call it optimization for dummies? How long did it take me to explain that to you? Half hour? I bet you every one of you could go to MATLAB now, get an objective function, write an evolutionary computation computer program. You might not have down exactly the mutation rate and the number of chromosomes in the population, but I bet every one of you could do, say, a 400 or 500 genetic algorithm solution to an objective function, which I gave you. Don't you agree? Yeah, go like that. Okay, so this is the reason that like fuzzy systems, it is kind of optimization for dummies. Is it the best way to find the extrema? Absolutely not. But the concept is very simple. The steps are very easy, and we can do great and wonderful things there. Now, there are clearly lots of variations of genetic algorithms in the area of evolutionary computation, and the way that you perform them is limited only by your imagination. Could you, for example, take this evolutionary computation, instead of using 1s and 0s, use -1s, 1s, and 0s? Yeah, it probably wouldn't be that bad of a thing, right? It's just that you have a 3-level sort of logic now to encode your numbers. You could do that. Do you follow? Instead of the chromosomes being zeros and ones, we have plus and minus ones and zeros, right? So what changes in the algorithm? I don't know. What changes in the algorithm? Well, the flips, the mutations. Now you have to have a probability of, say, a -1 staying where it is, but now your options are to go to 0 or -1. So you have two different probabilities that you have to specify in terms of the mutation, right? Could you do it for, instead of ones and zeros, do a byte for each one of these? Yeah, you probably could. And instead of adding just one of these transitional probabilities, can you add maybe just a little bit of Gaussian noise of a certain variance in order to perturb and to affect the mutation? That's a very common way to do it also. I will mention in the literature that there's lots of controversy concerning the crossover. And this is something which is always, it hasn't puzzled me, but I have a hard time with it. Let me explain you why. It might be that I'm in a rut. You know, they say if the only tool you have, California Supreme Court Justice was the first to say this, if the only tool you have is a hammer, everything looks like a nail. I'm kind of in that situation. I like to visualize my error surfaces as something which is nice and smooth in a weight space. In a way, we're not doing this. What is this? This is a vertice of a hypercube, isn't it? And actually what we're doing is we're hopping around vertices of hypercubes when we go from 0 to 1, right? What I would like to see, and let me tell you, in fact, an evolutionary approach that I've used in some of my work. I would like to actually see something more of this form. Suppose that you mated two surviving chromosomes. It makes more sense to me to kind of draw a line in here and maybe, number one, pick a point which exists in the intersection of it, and then two, maybe perturb it a little bit in the orthogonal direction, something called the null space of the space, so that we get an offspring which is here, which is at least geometrically in the same ballpark as the two parents. Notice that we have no concept of that over here. If we have two chromosomes which are being represented as Boolean functions, we have 2 points for the hypercube, and then in the crossover process we pop to a third dimension. That has no guarantee at all of this geometrical kind of weight space that we're talking about. We're hopping around again on the vertices of a hypercube, which I have a more difficult time visualizing. Okay? So there isn't this smooth sort of transition. Notice another thing nice about it, it requires no derivative information. This is true of many evolutionary programs. There is no derivative concept here. Steepest descent, we have a derivative in order to figure out which way would be downhill. Now, do you think if you spent a little bit of time, maybe you could work a concept of a derivative into this program? Say you were using floating point instead of binary. Couldn't you not only do this, but before maybe they mated, have everybody take a step downhill? That makes sense? Take a step downhill and then do the next result. So the point is that the overall concept is very nice for the introduction of heuristics and different ways of doing things. Let me get back to the controversy of the crossover. There are some people that believe that this crossover does not belong there, and they actually omit this in their actual genetic algorithms. There are others which swear by it, and they always put it. And then there's people like me that kind of do it half and half. I take half of them, cross over. I don't know. I haven't made up my mind yet. But it's almost like there's different camps, unfortunately. The first IEEE transactions on evolutionary computation took place, I believe, in 1996. And before this time, all of these evolutionary camps had existed separately and had actually kind of battled each other. They each had different journals. They each were saying that their technique was better, and they had very, very little cross-communication in themselves. And in 1996, at the IEEE World Congress on Computational Intelligence, one of the sub-conferences was the IEEE International Conference on Evolutionary Computation, which was agreed by all of the different camps to be this little umbrella under which everything would exist. And each one of these people will tell you that their technique is best. Okay, you should use crossover, you shouldn't use crossover. Where in fact, I think that the reality is in the actual problem. I think it's, by the way, that's always an out, isn't it? It's a problem dependent. So I think it's a sort of error surface that you're dealing with, you're going to get different sorts of results. Okay, any questions on this? Okay, if you want to read more about this, this is in chapter 11 of your book. Now, how will we use this to train an artificial neural network? Is there a way we can do it? Yes, not only is there a way we can do it, but there's even more clever things that we can do. Now, I'm going to present the training of the neural network from the guise of a genetic algorithm. That is, looking at it from training a genetic algorithm. But please keep in mind any of the multi-agent techniques which you run across are applicable to this, any search sort of techniques that you are interested in. How would you train a neural network? Well, let's look at a neural network. What is the error in the neural network? It is equal to the summation over P, the summation over I of your outputs minus your targets squared. I think we put a half here. That's the error. Well, this is something we don't want to minimize, so let's actually make the fitness equal to e to the minus alpha e. By the way, another way we mentioned to address the problem of the algorithm not converging is to make your fitness function flatter. Can you say that fast 3 times? Make your fitness function flatter. How can we make our fitness function flatter? How do you make your fitness functions flatter? What would you do? Well, one thing you could do is play around with this alpha. If this alpha is in one range, it's going to be, what if this alpha is 0? That's pretty flat, isn't it? Right? If it's 0. If it's 0.01, well, it's not as, starting to get a little structure. If it's 1 billion, you got a pretty hilly fitness function, right? So you can play around with the value of alpha. And if one of your local minima is too deep, you can make it a little more shallow by playing around with the alpha. So here's the concept. We do this. Now, what is this error function a function of? It's a function of all of the weights associated with the program. And we're going to take all of the weights, we're just going to put them in a vector, and we're going to call this big, long vector of floating point weights W. And that contains all of the weights in the neural network. Doesn't matter what doesn't matter what architecture is. There's a value of W that you can put these here. And so you have the weights as equal to, well, weight 1, 1, weight 1, 2, weight 1, 3, weight 2, 3, weight 2, 4, etc. So you take all of these, and in some manner that you would like is to look at the weights this way. Now what you would like to do is you would like to put the weights on some sort of binary encoding technique, right? So maybe we could assign each weight a byte of accuracy, and if we did this, weight 1 might be 0, 1, 1, 0, 1, 1, 0, 1, okay? For that byte of accuracy. You need a sign bit too, because this weight can clearly go negative also, right? You can assign each one of these a 1 byte value, etc. And so you have this weight, and the way you initiate your process is just like with the conventional neural network. This is a search process. Specifically, you take your weights and you form a number of chromosomes, say weight 1 all the way down to weight 1,000, for example. Okay? And how do we generate these initially? Same way we generate them when we're using error back-propagation. We have to have some way to initialize the weights. These are typically done by random number generators. You got to make sure that they're not too big or you're going to saturate. They got to be just right. And these are our initial weights. And here we start.
That sounds just be a vector, is it?
I'm sorry, this should be transpose. It's a vector in the sense it's a sequence of 1s and 0s. Okay? It's a vector of 1s and 0s. So that's just how I'm keeping track of my chromosome. So we start out with 1,000 chromosomes, and then what do we do with these chromosomes? We compute the fitness associated with them. We look at the neural network with this weight, and we compute the corresponding fitness, and this might have a fitness of 52 and 46 and 10 to the fifth or whatever. And there's our fitness, and then we do the other processes. We do the survival of the fittest, we do the crossover, we do the mutation, and we continue from iteration to iteration. On this, we mentioned that it was important in training a neural network to keep track of the generalization. Is there a way we can keep track of the generalization on this one? Yes, there is. We can look, for example, as a function of the generations, we can look at the fitness, and the fitness should, well, let me look at the error, because the error is what? Minus 1 over alpha times the log of the fitness, something like that, never how you solve for it. So the error begins to come down, and eventually you might get this. And you'll find for a while, especially if you do King of the Hill, you have very long flat spots in here, because things will be bubbling underneath, but your fitness is actually going to be done by your King of the Hill. So your King of the Hill is just going to get it flat, and then all of a sudden there's a rebellion from underneath, and they knock the King of the Hill off, and boom, it comes down here. So these are typically, in the beginning it's going to be, as you find new and new better results, it'll be kind of continuous, and then it will begin to come in step-sized packages, and eventually you'll get flatlined out here to a point. Well, you have this, but notice that every time that you do every time that you generate an error, and this error is your training error, you can also generate a test error, right? You can also generate a test error. And just like in the neural network trained with error back-propagation, you can choose where this begins to flatten out and go up and choose the corresponding weights there. Now, this is not a technique which is used as extensively, and I've not seen it used a lot successfully in the training of the neural networks. The error back-propagation, this idea of following the two curves, is very, very standard, but here it isn't a standard. But nevertheless, we can see that in any of these algorithms that we can always monitor the test data, the test error versus the training error down here. And we don't want to let this training error get small at the cost of the test error going up, because again, what have we done? We've memorized as opposed to learn. Okay. Now, here's something which is intriguing. This is, unfortunately, doesn't work really well. But it's a compelling idea. By the way, can you see that this is going to take a lot of computer power to do it? Well, that's what you get for being a dummy. Okay, this is optimization for dummies. You're trading off your intelligence and your domain expertise to give it computationally to the computer. That's why they call it computational intelligence. The computation goes on the computer and less on the front end. Question? There was a question.
I'm confused as to why the curve is always going down, since there's a big random component. It seems like it's only going up and down.
Okay, good point. The reason I have it going down is because I'm keeping a King of the Hill here. Okay, so every time I keep the best one. So I know my next generation has to be at least as good as my previous if I use King of the Hill.
So you don't cross over on him.
Well, yeah, but I might duplicate them to do it, but I keep one pure blue blood up here, okay, in order to dominate. Yeah, good point. Here's another idea. By the way, if you have a computer power and Moore's law stays into effect and we keep doubling computer speed every 10 months, are we still on Moore's law curve? The idea that computing power doubles every 10 months? What? Was it 3 months?
It's like 18 months.
18? Oh, we're ahead of that.
And memory is every 3 years.
Yeah, okay. I think we're way ahead of that, every 3 years. But here's something which is really interesting if you did this. You know your weight vector, where you have weight 1, 1, weight 1, 2, weight 1, 3, weight 2, 1, out here. Okay, so we finish up the weight vector, right? Now what we're going to do is we're going to put in something else. We're going to put in the number of layers, Okay, can we do that? The number of layers. We can put in the number of values for each layer, and then make sure we have enough of these weights so that it fits this. And we can actually, by doing this sort of thing, actually do a genetic search where we not only are able to train the weights, but if you do it in a clever manner, we would be able to choose the architecture of the neural network, which would give us the best result, which is kind of interesting. Now, what do we do if we use backpropagation? We want the best architecture. We haven't addressed that yet. It's actually, the way that it is right now, is kind of a time-consuming sort of process. We will talk about a concept which is known as generalization. Which is obtained through a process called regularization. Which can allow us to pick the best architecture, or at least take a overfitted architecture and tune it down into something which is palatable. I think we're running out of time, so any additional questions? Okay, the test is due beginning of period next time, right? Okay, thank you for your time. You're dismissed.